Let's see if we can make some sense out of the area formulas for triangle, rectangle, parallelogram, and trapezoid based on what we can figure out from this triangle. So we have triangle ABC, currently a right triangle with altitude drawn from B to the line opposite B, which is in this case AC. And we'd like to start remembering that the area formula for a triangle is based on the area for the related rectangle. So let's go ahead and rotate this triangle around the midpoint of the longest side, 180 degrees. So we know that this triangle is a copy of this triangle. We started out with a right triangle. So the copy is also a right triangle. We also know that this angle here at BAC is a copy of this triangle here, and this angle here is a copy of this angle here. Because this triangle is already 90, we know that these two angles in the right triangle are acute, and their copies must also be 90. So we know we have a rectangle here, and this is the related rectangle, and let's capitalize that. The related rectangle is called related because it has the same base and the same height as the triangle, which allows us to borrow the measurements to find the area of the related triangle. So in this case, the base runs here, this segment from B to C, where the reflection of A is, and the height runs from B to C, or at least one of the heights runs from B to C. And that height is marked here because I have all three heights marked in green. So exactly half of the area represented by the related rectangle belongs to the area represented by the original triangle. So let's move over to the acute triangle. Remember this guy? Let's not go quite to the isosceles, although that's a fairly pleasing triangle. But let's go over to the acute triangle where all three angles are acute and the altitudes or heights all land inside the triangle. And the reflection of original triangle ABC to A prime, B prime, C prime, still congruent. The image is still congruent to the pre-image. We can still construct a related rectangle that has the same height and the same base. The translated vector. Let's just take this height we're going to select an object to translate, then select a vector. And now we need the same base. So let's translate this base segment. Segment A is what we want. And we want to translate it along this vector. So for this triangle, the related rectangle runs through these 4 points because it's made from the same height and the same base. Let's see if we can get an image of that, and we can here. The related triangle is exactly half, and we can show that by a rotation around the midpoint of polygon 1 through midpoint of M, 180 degrees. We can show that the copy is in fact half the area of the related rectangle. And that related rectangle works out pretty well for the acute isosceles, and even for the obtuse. The base here in pink and the height here in green are still the same from rectangle to triangle because they've been made with a translation. So the related rectangle does not necessarily need to land inside the triangle. But the area of the triangle with the same base and height will always be half the area of the rectangle with the same base and height. So let's see if we can figure out why the parallelogram also borrows its area formula from the rectangle. I'm going to create a rectangle by rotating this polygon around the midpoint of the long side, or this right triangle around the midpoint of the long side, and I'm going to make it into a polygon with the polygon tool. And then we can turn off. No, I don't want to turn off that object, so let's put that back on. But I can turn off some segments here. So I've got this great looking rectangle here that can also be dragged into a parallelogram. Now, how do I create a convincing argument that the area for this parallelogram is the same as the area for the rectangle? I have an idea. Let's convince ourselves that this is the height of this parallelogram. By making sure it's perpendicular. And let's translate this height by a vector. And let's translate this base, this segment, along this vector, and let's create the related rectangle. Now, I'd kind of like this related rectangle to show up separately. And what do you see here? If I convince you that this triangle is a copy of this triangle, would that work to convince you that we can use the same area formula for this parallelogram that we can use for the related rectangle? How about that? Does that do it? So the rectangle with the same base and height as the parallelogram can be used to find the area formula. Now the one that might be a little trickier is the area formula for the trapezoid. Is it clear? How do I decorate this height segment in such a way? Oh, I'm decorating a whole polygon. I don't really want to do that. But how do I decorate this height segment? Is this segment J sub 1? I'm just going to find J sub 1 over here and change the properties of it. Let's give it a bright red. Fancy. Thick line. Well, that's crazy. Not what I meant to do at all. Well, this is a pretty good looking height right here. Is it clear that the height is the perpendicular segment from a vertex of the parallelogram to the line containing the opposite side? What I want to avoid is having students use this slanted measure as the height. It is not the height. This measure right here is not perpendicular to anything, so it doesn't fall into the definition for height. I must use this perpendicular segment. So I have this lovely parallelogram, and I have a segment from G to H that I'd like the midpoint of. So I'm going to use the midpoint tool to get a midpoint for F sub 1. I'm going to go ahead and draw a segment from here to here and just create a general trapezoid. Remember that a trapezoid is a figure with one pair and only one pair of parallel lines. It's a quadrilateral with only one pair of parallel lines. Maybe I need to turn this guy off. And there's a bunch of other stuff I can turn off too. So if I were to rotate this trapezoid around point L, I have copied this figure, so this angle is the same as this angle. This angle is the same as this angle. This pair of bases added together is congruent to this pair of bases added together. So the figure K, H prime, K prime, H is in fact a parallelogram. And it's a parallelogram that has area that's exactly 2 times this trapezoid. So if I were to know the area of this large parallelogram, couldn't I divide it by 2 and get the area of this smaller trapezoid? Well, I can do that by translating the height from here to the new related rectangle and translating the base and creating the related rectangle. Are you convinced?